Welcome to AP Calculus AB video for skill number 111. I can write and evaluate exponential and logarithmic expressions to model growth and decay situations. And featured below is the Parthenon, and the trivia question for the video is, what was on the hill before the Parthenon? We'll start our notes on page 111A. And for this video, I'm just going to show you two examples, one modeling exponential decay and one modeling exponential growth. So example 1, suppose that the half-life of a certain radioactive substance is 4,500 years, and that there is a 8,000 kilogram leak into the sewer system. When will there be only 5 kilograms of the substance remaining? So if I started to rationalize through this, since we start with 8,000 kilograms, after 4,500 years we'll have half of that. If we go for a total of 9,000 years, we'll take the 8,000, we'll cut it in half, and then we'll cut it in half again. If we go 13,500 years, we will take our 8,000 and we'll cut it in half 3 times. So if I wanted to model this after t years, I'm going to do 8,000 times 1/2 to my t divided by 4,500. And I divide it by 4,500 because each cycle is 4,500 years. So now what I've done is I've created an equation which models the decay of the radioactive substance. And the question is asking us to solve for when will there be 5 kilograms of the substance remaining. So it would be really good if we could solve this with a grapher. In fact, the textbook generally is asking us to solve for the with a grapher. And what that's saying is plug your equation into the grapher and then solve for when the curve is crossing a y height of 5. So if you set your y min to 0 and your y max to 10, and then you're going to probably have an x min of 0 and an x max, I don't know, it could be anywhere upwards of 10,000, 20,000, 30,000. It's really hard to predict how high we need to go, so maybe we stick it at 1 million just to hopefully capture that point. And if we do that, we probably are going to get a graph which looks something like that on the screen. However, solving it graphically is sometimes tedious because we're trying to find that window that works. So I encourage you to solve it algebraically. And what we can do here is we're solving for 5 equals our model. And so in the first step I divided both sides by 8,000. In the next step, in order to get rid of the exponent, I took the natural log of both sides. And I'm leaving this as a fraction because the decimal is really, really small. When I've taken the natural log of the right-hand side, I can actually move the exponent down in front. That was one of the log properties that we should remember. So then, in the final step, I'm able to multiply by 4,500. So if I multiply both sides by 4,500, that's going to cancel out the denominator. And then if I divide both sides by ln of 1/2, then that's going to cancel out the ln, and I'm left with just t on the right hand side. If I plug this final answer all into a calculator, I will yield an answer of approximately 47,900 years. And that's how long it'll take for the 8,000 kilograms to decay to 5 kilograms, which is pretty frightening because the half-life of some radioactive substance are that big, and we have spills that are larger than that. Alright, for example 111b, for example 2 on page 111b, we're looking at exponential growth, and A very common scenario of exponential growth is continuously compounded interest. And we should recall that the formula for continuously compounded interest is our principal times e raised to the RT. And we're being asked how long will it take for a $10,000 investment to triple in a 5% account and a 10% account. There should be a question mark there. So what we're going to do is we're going to take our continuous compounding equation and we're going to substitute values in. Because we're starting at $10,000 and we're trying to triple it, we would arrive at $30,000 and our interest rate is 5%. And it's important that we remember to convert the percentage to a decimal, because if we don't, we will get the wrong answer. So the first thing I did was I divided both sides by 10,000, and that gives me 3 equals e to the 0.05t. Then to get rid of the e, I took the natural log of both sides, natural log of 3, and if I take the natural log of the right-hand side, I can use my logarithm properties to take my exponent and move it down in front. And then I recall that the natural log of e is 1, so that cancels out, and I arrive at natural log of 3 equals 0.05t. Divide both sides by 0.05, and I get my final answer. And that's not very informative to me until I plug it in and get an actual numerical value of 21.972 years. So it takes approximately 22 years for my investment to triple at 5%. Doing the same process for 10%, we work through the same process and we get the equation and we find that it takes about 10.986 years, which if you notice is half of that value. So it makes sense that if I'm making double the interest, I should be able to make my account grow at twice the speed. Thanks for watching the video for Skill 111. I can write and evaluate exponential and logarithmic expressions to model growth and decay situations. And the trivia question was, what was on the hill before the Parthenon? Well, before the Parthenon was what we call the pre-Parthenon or older Parthenon, and that was destroyed during a Persian invasion in early around 480 BC. So it was replacing an old temple. The current Parthenon is representative of perhaps the pinnacle of the Doric order with its architecture.